So if I say the theoretical probability of an event, we're talking about the ratio of the number of different ways an event can occur divided by the total number of possible outcomes. So here's an easy example. What's the theoretical probability of getting a 2 as the outcome when I roll one die? 1 over 6. Yep. The probability of getting a 2 is 1 over 6. Because there's only one way that event can occur, but there's 6 possible outcomes on my die. Okay? This is pretty tricky. This next question. What's the theoretical probability of getting an 8 when you roll 2 dice? So if I roll 2 of them and I add it together, what's the probability that the sum is going to be 8? If you want to answer this question, I would make a table like this. And across the top, I'm going to list the outcomes for the first die that you roll. And then on the side, we list the outcomes for the second die. And each one can have one of 6 possible outcomes. It could be a 1, a 2, a 3, a 4, a 5, or a 6. And so I'm going to make this into a grid. And we'll be able to see that every box in this grid represents one of the possible outcomes of rolling 2 die, right? So filling this in, if I have a 1 plus 1, that's a 2 plus 1 is 3 plus 1 is 4, and so on. If I have 1 plus 2, it's 3, 1 plus 3 is 4, and so on. A 6 plus a 6 is a 12, and then I can keep filling these in, right? What I get from adding the row plus the column. And what you would probably notice as you fill this in is that all of the 8s are going to be on this diagonal, because I could get an 8 by rolling a 6 and then a 2, or a 5 and then a 3, or a 4 and a 4, or a 3 and a 5, or a 2 and a 6. So how many different ways can I get an 8 if I roll 2 dice? 5. Yeah, there are 5 different ways to get an 8. So that goes in the numerator. How many total possible outcomes are there? 36. So the probability of getting an 8 is 5 over 36. That's the answer. And we call this the theoretical probability because we're just taking the number of ways this event can occur divided by the total number of possible outcomes. What is the theoretical probability of getting 2 number cards that add to 15 when you draw 2 cards from a standard deck of playing cards? Assume that you're going to replace the first card back into the deck and shuffle again before drawing the second card. So it's kind of a similar situation, a little bit. You can imagine trying to draw like a bigger table where you have like ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And then the same thing along this side, ace, 2, 3, 4, and so on, right? So it's the same table that we drew before with the dice, but this is just a lot bigger. And then you think, how many different ways can I get cards that add to 15? I could get a 5 and a 10. And I could get a 6 and a 9. And I could get a 7 and 8. Or an 8 and then a 7. Or a 9 and then a 6. Or a 10 and then a 5. So that's 6 possibilities. And so that would be in my numerator. There's 6 different ways where I could get number cards that add to 15. What is the total number of possibilities? Again, if I was going to count up all the squares in this entire grid, then how many total possibilities are there?
$169.
169? Yeah, because it's 13 times 13, right? There's 13 cards from ace to king, and then you multiply that times 13, because this is a rectangle with width 13 and height 13. I guess it's a square. And then 13 times 13 would give me the area, or the number of little squares in this entire box. And 13 times 13 is 169. So that's my probability. And you might say, well, there's not just 13 cards in the deck, there's 52 cards in the deck, but you can simplify, right? Because the 52 cards are really just the 13 cards repeated 4 times. And so it's a simplifying assumption to just treat it as though there's 13 cards in the deck, because you have that symmetry. Okay, but again, that's the number of possible ways this event can occur divided by the total number of possible outcomes. So 6 over 169 chance that you draw 2 cards and they add together to get 15. Maybe that information is useful if you play like blackjack. I don't know. Maybe it's not. So theoretical probability is making our best estimate about what should happen. That's why it's theoretical, based on like these first principles. Empirical probability is different. Empirical means we've already taken a bunch of observations of a random process, and we're going to look back at what did happen and try to infer probabilities from the data we've collected. So empirical probability has this formula. It's a ratio again, but this time the numerator is the number of times a particular event occurred. There's a little typo there. The number of times a particular event occurred divided by the total number of outcomes that we sat and observed. So in the last 800 times that someone has played the airport slot machine, there have only been 6 jackpots awarded. If you decide to sit down and play one time, what's the probability that you're going to win? Yep. This is not a trick question, right? This is, we observed the event occurring 6 times out of 800 total outcomes that we observed. So the empirical probability is 6 out of 800. Suppose you are playing Yahtzee, and if you've never seen Yahtzee before, it's a game where you roll dice. It's not very exciting, but you're rolling dice. And you think that your friend is cheating, so you say, "You cheater, you are using a loaded die." So a loaded die is a dice that looks like an ordinary dice, but you put like a lead weight near one of the sides, and that way it always comes up 6 or something like that, something you desire. How could you test the die and resolve your dispute? And one way you could test it is you could, take the die you think is loaded, and you could grind it up into a fine dust and look for a lead weight. But what if you don't want to destroy your property? What if you don't want to destroy the dice? What would you do?
Weigh it.
Oh yeah, I guess you could. That is not exactly the answer I had in mind. Can you think of another way you could test this out? You roll it over and over again. Because we have a theoretical probability of rolling a 6. It's a 1 in 6 theoretical probability. Okay? So the theoretical probability is that it should be a 1 in 6 chance of getting each number. Then we would want to compare it against an empirical probability. An empirical probability means you actually have to sit down and roll the dice a whole bunch of times. Not just 6 times, but you might have to roll the dice like 600 times. And if we were to roll the dice 600 times, we don't expect that it's going to be exactly 100 over 600. Because that would actually still be a low probability thing for it to be exactly 100 out of 600. But we expect it to be something close. Like maybe it wouldn't be bizarre to see something like 103 out of 600 times. That might still be within the realm of reason. But if you ended up rolling this dice 600 times and it came up 6s 450 times out of 600, that would be extremely strong evidence that you had a loaded die. Okay. If I say this, if I say the words law of large numbers, this is what I'm talking about. If you go to measure the outcomes of a random process, your empirical probability might deviate from the theoretical probability if you only have a small number of trials. But if you have a really, really large number of trials, then as the size of your sample increases to infinity, the empirical probability will converge to the theoretical probability. And a way that we can illustrate this is to use Excel. And we're going to make a little simulation where I pretend I'm rolling a die. And I'm going to use rand between 1, 6 to get me a random outcome between 1 and 6. And so as much as I want to, I can generate random outcomes from my die. And like I said, if I only do this a few times, like maybe I do this 18 times, I don't expect the number of 6s that appear to be, exactly 3, right? There should be 3 if I do this 18 times. 1/6 times 18 is 3. And so there should be 3, but I don't have to always get 3, even though I know the way I set this up is a completely fair experiment. So I've got a large deviation between my empirical probabilities and my theoretical probabilities because 18 is still a really small sample size. But the idea is, what if we don't do this 18 times? What if we do this a lot of times? And a lot might be like 600 or 1,000 or more. I don't know. Just take a big, big, big sample of dice rolls. And now let's calculate the empirical probability here. And it should be pretty close to the theoretical probability. Maybe not exact. Oh, wow, that's really unlikely. But every time I rerun this experiment and I throw another 2,000 dice, I keep getting numbers that are close to the theoretical probability. And as I repeat this with more and more, not just 2,000, but 20,000 or 200,000, then you get exactly the theoretical probability. That's the the law of large numbers. Okay, this might also be obvious, but you should know this. The probability of any single event must be between 0 and 1. Think of how we defined theoretical probability. It was the number of ways it could occur divided by the total number of possible outcomes. So that ratio has to be between 0 and 1. Same thing, think about your empirical probabilities. The way we defined the ratio has to be between 0 and 1. You can't have a negative probability. You can't have a probability greater than 1. And then the next thing is if I add up all of the possible outcomes, if I add up the probability of each possible outcome, add them all together, that has to add up to 1. If we say the words subjective probability, subjective means it really depends on the subject. It depends on who's talking. It's more of an opinion than anything. So if your dad tells me there's a 30% chance the Royals are going to win their next baseball game, that's just your dad's opinion, right? Somebody else might give you a different percentage probability. That's a subjective probability. But sometimes, in fact, a lot of times, subjective probability is the only thing we really have to go off of. In particular games of chance, like poker and blackjack and rolling dice, whatever, you can calculate theoretical probabilities. And in certain situations, you can calculate empirical probabilities if you've gone ahead and made the observations. But what about like the next Chiefs game, when the Chiefs go to play their next team? You can't rely on theoretical probability, because in theory, there's two possible outcomes. They either win or they lose. And so theoretically, they have a 1 out of 2 chance of winning the game. But that's not informative. Saying a 50% chance of winning, that's not informative. You could use empirical probabilities and think, okay, how many games this season have the Chiefs won out of the total number of games they've played? And you can calculate an empirical probability. But that still loses out on a big piece of information, and that is they don't play the same team every time. They play different teams, and maybe next week the team sucks, or maybe next week the team is really, really a tough team. And so that would change your subjective probability. And then injuries also play a major factor. How many players are injured from one week to the next? That would factor into somebody's subjective probability. So a lot of times these are still really important, even if it's not very scientific. The word disjoint means mutually exclusive. So I would say that 2 or more events are disjoint if they have no outcomes in common. Here's an example. If I were to roll a die and I define one event like this, event number 1 is just saying that the outcome on the die, the face-up value, is going to be less than 3. So in other words, this could include rolling a 1 or rolling a 2. Event number 2 says the value on the face-up is going to be greater than 4. So that could include rolling a 5 or rolling a 6. And I haven't explicitly told you these definitions, but it's important to know an event in probability can include more than one outcome. So rolling a 1 is an outcome, rolling a 2 is an outcome. This event includes both of these outcomes. And the question is, are these events disjoint? Yes. They don't have any outcomes in common with each other, so they are disjoint. These are disjoint events. If you are asked to draw a Venn diagram, this is my circle that represents E1. This is my circle that represents event number 2. And then I would fill it in like this. I would say event number 1 has the 1s and the 2s. Event number 2 has the 5s and the 6s. Outside of this, not belonging to any event would be like rolling a 3 or rolling a 4. But notice there's nothing on the intersection between these circles because they don't have any outcomes in common. So if your events don't have anything in common, that makes them disjoint. Here's another one, another example. Suppose you draw one card from a standard deck of playing cards. Consider these two events. Are these events disjoint? Event number 1 is drawing a king of any suit. Event number 2 is drawing any one of the clubs. Are those disjoint events? No. What's the outcome that we have in common?
King of clubs.
Yeah, you can draw a king of clubs, and that's both events. And so if I was going to try to draw a Venn diagram here, here's E1, here's E2, and some of the things that I have I could list are like drawing a king of spades, drawing a king of hearts. In event number 2, I'm drawing any club, so I could draw a 2 of clubs, I could draw a 3 of clubs. But the overlapping outcome that belongs to both of them is a king of clubs. And obviously there's some that don't belong to either one, like a 7 of hearts or an 8 of diamonds. And I'm not going to list all 52 cards, but that's the idea. Since there is at least one outcome in their intersection, we say that these are not disjoint events. By the way, when I use the word intersection, this is what I'm talking about. This little symbol means intersection. And you're going to see that again. This is going to appear in formulas coming up. So make sure you know. It kind of looks like an N in a way. Not exactly, but it sort of looks like a lowercase n. Just to help you remember that it's an intersection. But an intersection is where two events overlap. And like I promised, that symbol is going to appear in at least this formula. Do you see my nice intersection symbol? For any two events, the probability of either event occurring is this. I can write the probability of event 1 or event 2 is equal to the probability of event 1 plus the probability of event 2 minus the probability of the intersection between these two events. What's nice is if two events are disjoint, they don't have an intersection, right? There's nothing in the intersection. And so this term becomes 0 for disjoint events, and it simplifies just to that. So we talked about this a moment ago, and we said that these are disjoint events. And that means the probability of E1 or E2 is going to be the probability of E1 plus the probability of E2. E1 has a probability of 2 out of 6. E2 has a probability of 2 out of 6. Add them together, and my probability is 4 out of 6, which I could also write as 2/3 if I want to. Okay, raise your hand if you have a question, so I can gauge whether we're going too fast or too slow. But here's an exercise. You draw one card from a standard deck of playing cards. What's the probability of drawing either a king of any suit or any one of the clubs? So I could call the king of any suit my event number 1, and I could draw my any one of the clubs as my event number 2. And what we're talking about is the probability of event 1 or event 2, and that should be equal to the probability of event 1 plus the probability of event 2 minus the probability of their intersection. Now, event 1 has 4 possible outcomes out of a total of 52. So there's my theoretical probability. Event number 2 has 13 possible outcomes out of a total 52 possible outcomes. And there's one little outcome that belongs to their intersection, the king of clubs. And so the probability of getting that king of clubs is going to be 1 out of 52. So I get 4 plus 13 minus 1, which will be 16 out of 52. And I can reduce that fraction. That would be like 8 out of 26, which would be the same thing as 4 out of 13. Okay. So maybe the most common mistake I might see on this next test is people forget to subtract the probability of the intersection. And they just do 4 out of 52 plus 13 out of 52 gives me 17 out of 52. But that would be wrong by just a little bit, because the mistake there is you're counting the king of spades twice. We're subtracting the intersection because we don't want to double dip. We only want to count the king of spades in there one time. Does that make sense? Okay. Use the following contingency table to determine the probability that a random selected U.S. resident is male. I'm going to need my calculator for this. I can already see it. Because I'm going to need the total number of males residing in the U.S. divided by the total number of people. And that's going to be 46 plus 63.3 plus 3.3 plus 12.1 plus 2.2. And if I did that right, it's 126.9. And then I'm going to add to that 40.1 plus 62 plus 11.9 plus 16.1 plus 3.1. And that's going to be 260.1. And maybe you want to divide, because those aren't nice fractions anyways. And this is about 0.49 when I round to 2 digits. So using this table, we figured out the probability of selecting a male is 0.49. What about selecting a widowed person? That would be the total number widowed divided by the total again. And the total widowed would be 3.3 plus 11.9 out of 260.1. That would be 0.06. What about this? If I say widowed or divorced, we're talking about this. The probability of this event or that event happening, widowed or divorced. And so it's going to be the probability of E1 plus the probability of E2. And the thing is, the way this contingency table is set up, widowed and divorced are separate categories. Are those disjoint events? Yeah, according to this table, those are disjoint events. There's not people listed in the table who are widowed and divorced. There's no intersection between those two categories. And so I don't have to even worry about the probability of their intersection, because there is no intersection. And so now we can say, well, the probability of widowed is 0.06, and the probability of divorced is going to be 28.2 over 260.1, so whatever that is. And then what do we have last? We have this situation where we want the probability of male or widowed. So tell me, are those events disjoint? No. So I actually do have to subtract their intersection. In other words, this is going to be the males plus those widowed minus the male widows over 260.1. Whatever you get from doing that in your calculator. And by the way, in your calculator, you can't just type in 126.9 plus 15.2 minus 3.3 divided by 260.1. Your calculator will do things in the order of operations. And that means that it will divide 3.3 divided by 260.1 and then add those numbers together, which is not good. If you want your calculator to do this correctly, you have to put parentheses around that numerator when you use your calculator. Otherwise, you're going to get the wrong answer, and if you do this right, well, it should be 0.53. Okay. And you would know if you got it wrong, right? Like, if you didn't use the parentheses, your answer would be something like 141. And hopefully you would stop and you would think, 141 is not a probability, right? It's greater than 1. So you got to kind of sanity check your answers and make sure you're on the right track. Okay, I see we're nearing the end. For an event, its complement, is a vocab word, is denoted with a little superscript capital C, and the complement contains all possible outcomes that do not belong to the original event. And so if I roll a die, and my event is that I get a 6, then the complement of this event is the set of outcomes 1, 2, 3, 4, and 5. So a complement contains all the possible outcomes that do not belong to the original event. That way we can say an event and its complement are disjoint because they don't have anything in common. If these are disjoint events and they cover the entire set of possible outcomes, well, you also know the probability that we get from adding up the entire set of possible outcomes has to be 1. And so we call this the complement rule. The probability of some event plus the probability of its complement is 1. And this one says, at your church picnic, you buy 1 raffle ticket for a new set of golf clubs. They randomly select 1 raffle ticket out of 50 to be the winner. What's the probability that you lose? You could think about this as the probability of winning, which is going to be 1 out of 50. 1 ticket has your name on it out of 50 tickets. Well, winning is like, let's say my E1. The complement of winning would be losing. So if I want the probability of the complement, I just have to do 1 minus 1 over 50, which is 49 out of 50. And this is therefore the probability that we lose and we don't win anything.